just so that people can do that. But yeah, I'm doing another very large recycling project because I just recently purchased a house, which fortunately for me happens to be just right across the street. But it was a hoarder's house, and what he was hoarding was aluminum cans, plastic bags, plastic bottles, and stuff like that. I actually hauled out nearly 300 pounds worth of aluminum cans.
Wow.
So I took them to the recycler, and the first recycler only gave me 15 cents a pound, which was going, wow, that's not very much for my 233 pounds. But the second recycler I took it to gave me 26 cents per pound. So, gee, I should have gone to the second guy, I guess, before. But still, I only made, let's see, I got 35 and maybe $16. So, maybe, $50 maybe for my cans and my efforts.
Uh-huh. Well, when I was a young fella, they used to give you 2 cents for a soft drink can and for soft drink bottles. And so I used to go collect them and take them to the grocery store and collect my 2 cents each and use that for spending money. And but they don't offer as much as they used to. They used to reuse some of them sometimes, particularly the bottles sometimes. So like the Coke bottles and Pepsi bottles and stuff like that.
Yeah, they don't have a deposit thing in Washington State, but of course I live in the Pacific Northwest where everyone recycles everything. There actually is not a bin labeled garbage. No, not really, but it would almost seem to be that way. You'll actually find that in cruise ships, is that they'll have all the recycling bins, but actually nothing labeled garbage. I guess you're just supposed to leave it lying on the table or something. But there is not actually a garbage bin, right?
Well,
there's a place
for that outside and let it decay and turn back into soil and fertilizer, whatever you want to call it. And so I do that, and that way I don't have to throw anything away. I just recycle and I reuse it after it decays. And, but my problem is I do my planting outdoors, and the deer like what I'm raising, and they come in and eat it. And even if I put a fence around it, they just jump over the fence and get it there and get it.
That's why you got to work on the indoor garden, like I'm working on here.
That's right.
I'm working on the indoor garden, and it is a remarkable thing that in the middle of winter you can go pick fresh peas and just, you can just eat them. You don't have to cook them or nothing. Just,
Right. And they're very good.
Yes, they're very good. Excellent. I think anything that you grow yourself just seems so much better. Or maybe that's like when you go camping. Anything you make when you go camping just seems to taste so much better, right? Even though it came from the dollar store, it seemed really good. Right?
Well, we should maybe have a talk sometime about them, because unfortunately our government, like in my area, I have a lot of Amish people. They raise food like you do for themselves to eat, but to sell, they're required to raise genetically modified food, and that's not good for them. And they know it's not good for them. They won't even eat it, but they raise it because the federal government requires them to, and if they don't, they take them to court and bankrupt them. And so I just think that our government is going off on tangent, and it's making us have the poorest health of the 37 industrialized nations in the world.
But now, what do you think what's going on with Monsanto? They're the inventors of the genetically modified wheat and stuff like that, and they're really taking it on the chin because apparently Roundup causes cancer, right?
Right.
How did that happen, right? You'd think Monsanto would have so much influence that they wouldn't care if people got cancer.
Well, the Food and Drug Administration, is the medical field and the agricultural field, and the agricultural field generates more business for the medical field, and so they like it. And that's not the way it should be. It should be for the benefit of the American public, and not give us stuff that generates more income for their business.
Yeah, but Monsanto is getting killed with all these lawsuits now. See, I'm surprised to see if they had as much control as you say they do, then they should be able to brush these off, these lawsuits, right? But probably the only people who are more powerful than the agricultural union would probably be the litigation lawyers, right? Maybe perhaps the litigation lawyers are more powerful than even the federal government. What do you think? Maybe that explains it.
Well, you have to give congressmen money to get them to vote for stuff, and so you have to have some money, whatever you do. And
yeah, they get it from Monsanto now, right?
Yeah, they may very well get it.
Because they go and they sue because of the non-Hodgkin's lymphoma. I guess people have been getting from using Roundup. Although I'm not exactly sure what the science is on that, but apparently billions have been awarded to people who have gotten cancer from that.
Uh-huh. Well, I know when the Amish raise corn, for instance, you can see the distance between the corn plants in the ones that they're going to eat. But when they raise it for sale to the grocery stores and other businesses like that, they get such a high density. They get 3 times the density of corn in the field, so they get 3 times as much. And the animals will not eat that corn. They'll eat their corn that they raise for themselves, but they won't eat this corn that they raise for.
You mean like the deer who come by?
The deer, yeah. But not only that, the insects won't eat it. So they don't lose as much to the insects and other animals. But they're smart enough to know it's no good. We're not. You think they would?
Yeah, I always wondered when I see those commercial corn fields, just how is it they get such high density? Because if you look in the package on the seed that you get for your own garden, they say, spread like 2 feet apart or something,
right,
or whatever that is. But it looks like they're just right up against each other as almost a solid wall.
Yeah.
In a commercial cornfield, you kind of wonder how even light gets in to the plant. They're so densely planted.
Yeah. Well, I saw a movie where a fellow was interviewing a man who worked for one of these great big farms, and his job was to drive the tractor down 1 row of corn and back, and that was 8 hours. And he had to use a special tractor that could keep track of where he was within 6 inches, so that he didn't, when he was planting them and everything, he didn't mess up or get into the pipes that were irrigating the plant. So they use a lot of irrigation. It's more efficient use of the water. And but he was asked to eat some after he got back by the fellow who was running the tractor. And when he ate some of the corn that had been harvested that was genetically modified, he says, "Oh, this is terrible. I can't eat it." And the fellow told him, "Well, the people that make cornflakes and all that kind of stuff, they process it as chemicals so you don't have this problem. You can eat it, you think. But it still has medical problems that show up on the long term."
Well, I was watching like a documentary, and it appears that our entire food chain is based off of corn, because they grow the corn, and then everything eats the corn, and then we eat the thing that ate the corn, and it's just and the funny thing is that you're saying that the corn that they grow is largely inedible, and it is that no one would ever eat the vast majority of the corn which is grown, because it's grown to be processed into something else. It's not like the corn that you would buy in the grocery store as corn on the cob. It's apparently this, completely inedible thing. They let it just dry up, and so they can just stick it in their silos, and then it gets made into Doritos or whatever. I don't know, or just fed to the animals.
Yeah. Well, it's interesting. Do you know where the corn came from? They didn't have corn in Europe for thousands of years. But
yeah, wasn't that an Aztec thing or something?
Yeah, when they came to America, that's when they discovered corn, and they took it back to Europe, and then corn became. And they also found potatoes. They didn't have potatoes, and between corn and potatoes, that was the food that a lot of people ate because it didn't. You could get more produce per acre. And see, in Europe, the population is growing such that they didn't have enough land to really do as much farming as they needed. In America, we had, at least in the colonial days, we had so much land, we didn't know what to do with all of it. But now we're getting more population, and the Amish are having trouble finding farmland. They sometimes have to move 1,000 miles or 2,000 miles to get enough farmland for their children. And they'll have to move and sell their old farm and develop a number of new farms. And it's giving them a hard time because they can't get enough land, so they're having to have their children go into other lines of work than just raising food, which is what they did traditionally. So they become carpenters and different jobs like that they can do.
All right. Well, it looks like we've got some people on the science chat. We've got some people in the live room, so 6 people can come into the live room. And so far, we have Bill who's been talking, Bob, and Stefan and Eugene. So I have you live on the program, and if you'd like to speak, or if you have some questions or bring up some topics, just unmute yourself and go ahead and chat. And but if you don't want to speak, you can free up that slot by just going to the YouTube link. But you're always welcome to come back in our lives, in the our live studio, so that you can chat. So me and Bill, we were just talking a little bit about my back here. I have my small garden here, which is made possible through the wonders of LED lights, because you got these super bright LED lights, and they're just pretty cheap. Like you can buy this like at Harbor Freight for maybe $20 or so. And the super bright LED lights, I mean, this thing is as bright as maybe 500 watt bulbs or whatever. And that would normally cost a lot of energy to run all the time, but these LEDs hardly take anything. So that was my experiment going on here. I went to Home Depot, just got a very large planter box, and filled it up with some dirt I got for $5 at Walmart. And I planted the Swiss chard, and I've had strawberries, and this year right now I have going on some peas, some snap peas, and some beans, and a cucumber plant. So maybe in about 2 months or so, then I'll have some fresh veggies here in the middle of winter. So that'll be kind of cool. I also brought in my fuchsia plant. So last year I let my fuchsia plant out in the winter time, and it just died. And then of course I had to buy another one for $20 later on. But I figured I'd save it this time. I'd bring it inside. I have some greenery to go by. And so we've been talking a little bit about raising food, and genetically modified food, and don't eat the corn, right? No, and about Monsanto and the use of Roundup, which is kind of curious because as near as I can tell, you can still buy Roundup, right? I don't think they've banned it, and I hope they don't, because I don't want to have to pull weeds. I mean, Roundup is amazing in that you can just spray it on the plant, and it dies all the way down to the root, and you don't have to, it virtually just disappears. But it's kind of weird the way that those things work. It's actually not a poison, right? It's not like arsenic or anything like that. It's actually a biological agent. It works by either shutting down a critical enzyme pathway for the plant, or it actually, another way it does it is it causes it to grow out of control. As if you were giving, I don't know, like the plant a cancer. So you spray it on there, and it'll just like grow and like all kinds of. If you look at it, like the dandelion will just get kind of distorted, and then it'll die off. But it's not an actual poison, which I thought was interesting. Because it could be a poison, you could spray something on it that just literally kills the plant, like it would kill people. But no, it only works on the plant tissues, so that's why they think it's safe. That's why the makers of Roundup, say, yeah, we could just drink this stuff; it'll be okay, right? They say it's not going to hurt you, except apparently, if you use enough of it, it gives you non-Hodgkin's lymphoma, right? And then you can sue them and get $1 billion, apparently, right?
$1 billion, maybe.
And we're thinking that the only people who are more powerful than the agricultural or medical lobby are the lawyers, right?
Right.
Who get the $500 million when they get the $1 billion settlement, right? They always get like 40-50%, right?
Right.
So I guess that's a pretty big incentive for them to go after them, even if they're the biggest lobby, going against the biggest lobby on the planet, which would be the agricultural lobby, right? So we've been talking about that, but we're just here chatting anyway. So did anybody else have any topics they'd like to bring up here? I'm just going to check the comments here. If you guys got anything that you'd like to, just chat about, that's what we're here for. So
Hello.
Hello.
My name is Eugene. It's
Hello,
my
Eugene.
first time for your chat. Nice to meet you.
Yes, did you you were the one who emailed me? You had a paper that you would like to present?
Yeah, I posted the link to the chat.
All right. Well, we can do that. Did you want me to put up your paper?
Yeah, if you can share the screen or something.
Yeah, okay. So let me work on that. But why don't you go ahead? Do you have a camera?
Yes, I do. I can switch it on, but I'm speaking through my camera, so it might be the quality of audio would be worse if I do that. But I'll try it.
Yeah, let's try it out. Let's see how that works out. There we go. We see you.
Oh, sorry. Hello.
All right. So why don't you go?
Somehow I don't see anyone else. How do I do it?
Well, you're in the live room, so you should be able to see. I mean, right now I've got you as the main picture there.
Oh, I see.
So I'm gonna go dig up your email here. So why don't you go ahead and introduce your idea?
Yeah. Okay. So basically, the paper is about my hypothesis, which I call biogenic earthquake hypothesis, which is essentially, it explores the idea that subsurface biosphere, let's say microbes that live under the surface of the Earth, might actually trigger earthquakes. So this is an idea in a nutshell, but the paper is pretty long. I mean, I have done quite a bit of research there, what kind of limits living beings have in terms of temperatures and pressures and things like that. And it turns out that all the previous estimates of, let's say, the maximal depth where microbes might live were severely underestimated. The current estimate, the latest one I was able to find was something like 12 or maybe 15 kilometers. But it's based on previous knowledge about the maximal temperature and pressure, right? But the latest papers, like in 2018, they show that these temperature estimates in particular are like underestimated like 3 times or something. So the most extreme organism that was known before 2018 was able to withstand 122 or maybe 130 degrees Celsius. But in 2018, they found another strain that was able to survive at 420, I think. So that already, you know, expands the possible limit for life in terms of depth. And in terms of pressure, I've also checked like the models of the internal composition of the Earth, and it seems to me that from the results of my research that the microbes might be living up to like 75 kilometers deep. So that's a reasonable enough depth to, you know, suggest that they might be involved in earthquake triggering, etc. But there's a whole bunch of other info in the paper. Like I discussed the possibilities for how can they acquire energy. In particular, I suggest that the various electrochemical processes might be involved. You know, they might like telluric currents, the currents that run through the surface, like through the Earth, basically, might be involved because we actually have it has been known that, let's say, under the surface of the ocean, I mean, under the like a bed of the ocean, how do you say it? There are bacterial collectives that basically produce what might be called distributed breathing or something like that. So the bacteria right at the surface of the bottom of the ocean, they have access to oxygen from the water, but the bacteria like under the surface of the ocean floor, they have access to sulfur, let's say. So they cooperate, they form kind of long chains, and the bacteria on the top, they intake electrons from the oxygen, or I'm sorry, vice versa. The bacteria underneath the surface, they take electrons from sulfur, transfer the electrons through this bacterial chain to the bacteria on the top, who attach these electrons to the oxygen. So it's basically a direct electron transport as the way of breathing. So they're basically feeding on electric current. So I suggest that this process might be also happening even like tens of kilometers deep in the Earth. And again, like modern estimates of biomass suggest that, well, there's a lot of stuff there, basically. I also give some estimates in terms of energy, like whether or not there is enough energy to produce an earthquake, like biochemical energy, let's say. And it seems to be valid, like even for the strongest earthquakes, like magnitude 9. But again, like the paper is really long. There's a lot of stupid ideas there, a lot of things that I've explored. So
Okay, well,
read, I guess.
I had put the link to your paper up here on the banner here, so that's eartharvix.org, BAE7T. Now I know about arvix.org, but what is eartharvix.org? Is that another Arvix?
Yeah, well, I think it should be pronounced like archive, like archive. It's just the Greek letter he, you know, kind of like H. So basically the thing is that archive.org was mostly about physics, like physics, mathematics, and things like that. And I mean, it's a preprint server, right? So you upload your papers that are not yet published, but you want them to be there to like claim priority or something like that. But this particular thing is focused on like geosciences, like whatever, geophysics, seismology, etc. Because again, archive.org is about physics and mathematics mostly. There is also bioarchive, which focuses on biology and medicine specifically. etc.
That's interesting. Yeah, well, I appreciate that they've done that. So the Arvix is Vixera backwards. So Vixera is the official mainstream preprint server, but
No, I think it's the other way around. It's actually archive.org is maintained by Cornell University, and it appeared like first. I think what happened is Vixera.org actually appeared after as a response to some of the moderating policy of archive.org.
oh yeah, that's
So-
right. That's right. Yeah.
Yeah.
Because in order to get on Arvix, you have to have like two college university sponsors at a minimum.
Well, I don't think it's about sponsors. So it's not about money. It's just about references. Like you cannot just register there, I think.
Yeah, you
Although
can't.
I'm
Well, that's what I mean. Is that
registered there, but-
you have to have two people basically endorse you,
Yeah,
right?
yeah, exactly.
Which would stop most of us crazy dissidents. So, which I suppose is exactly what their intention is, because we are all crazy, and probably 90% of everything we do is just crazy. But at some point, the 0.005% might actually be right or revolutionary. That still gets filtered out. So I think like most things is that you can't filter out the good stuff without getting the bad stuff. So there's just no way to do that.
Perhaps. Yeah. Well, I've actually found these preprint servers to be the best vehicle to publish stuff. Like formally, I've submitted this paper to one of the major journals, like the Journal of Geophysical Research Biogeosciences. But I'm absolutely sure it's not going to be published because, like, if you look at some of the references I have there for like Hollow Earth by Jan Lambert and things like that, and like biogenic elemental transmutations, etc. So that would never be published. I'm absolutely convinced. Like at best, they would ask me to like delete one half of the paper because it's too radical.
Really, I think I tried doing that as an experiment once, and they always sent you this nice, polite letter saying, "This is outside of our interest," right? Like physics. So.
Well, yeah. Well, so far the only response I've had was formal, like, "Oh, you don't have like a data availability statement. You don't have this. You don't have that." Well, I've added all that and resubmitted, but they didn't answer since then. That was like a month ago already.
Yeah, they're analyzing all your data, right? Maybe, or they're just still laughing. So, I mean, it is kind of a wild idea, but that's what the John Chappell Natural Philosophy Society exists for. Since we won't laugh at you, at least in your face, but maybe later on. But
fair enough.
But this is an interesting idea. So you're thinking that earthquakes are perhaps caused by biological activity, and some of these things are hard to believe. It's like probably the thing that the geophysicists would say that, well, why do we need to have some other cause for earthquakes when it's clearly plate tectonics which causes earthquakes? So why would we need to consider this other idea?
Well, one interesting thing I found while researching this was that it seems, according to even the mainstream geophysicists, plate tectonics didn't exist before Archean Eon, which is exactly when life appeared. So the appearance of life coincided with the appearance of plate tectonics. And well, you might claim, of course, that plate tectonics helped life to appear somehow, like through some stochastic processes, but maybe it was the other way around. Maybe it was life that produced these cracks or whatever.
Well, how do we know that? I mean, these are the kind of questions that's I wasn't back then there. Then no humans were back there. When did life start? That was how many millions of years ago?
Yeah, I actually even have another question. Did life even start in the first place? I mean, there's just no proof that life, let's say, didn't exist eternally. You cannot prove that fundamentally. You can only like make conjectures, let's say, according to our current dating methods, etc. Like the oldest fossils are, let's say, appear to be 4 billion years old, but well, how do we know that, let's say, decay rates are constant? We actually know they're not constant, you know. I mean, nuclear decay, like C14 dating, things like that.
Well, I suppose the way that they would do it is that they could find fossils and then they could date the rocks around the fossils, and then they could estimate how long plate tectonics has been going on for. I mean, how long is, I mean, that was another thing that I don't think would have a beginning, which is plate tectonics. I would think that would have happened from day one on the planet Earth, or is there evidence that there was no plate tectonics and then at some point it started up?
Well, yeah, this is exactly the point I was making. It's not my discovery. I actually referenced one guy right there in the introduction. Like, I think it's one of the first references I give is to the paper that says that plate tectonics didn't exist before Archean Aeon.
Well, I'm not sure how they would justify that. But
I don't know. Like, read the paper of this guy.
Let me see. I'm trying to switch to application window. It's not showing my other screen here.
That if you want, Franklin.
Pardon?
The plate tectonics, in the work that I've been doing, I've derived the force of gravity from electrodynamics, and the force of gravity is due to the force being vibrating multipoles, electric multipoles, like dipoles, and they have to radiate continuously because the charges in the atoms and nuclei that are moving back and forth, vibration, are accelerated, and anytime you accelerate a charge, you have to radiate. And so that radiation is occurring, and in the Earth, for instance, the radiation from the things in the center of the Earth, that radiation gets reabsorbed before it escapes from the Earth, but the matter that's on the surface of the Earth can radiate out into space, and that energy is lost. And when it's lost, the force of gravity decreases and decays, and that causes the Earth to expand. Just like you had a balloon full of hydrogen and you let go, it'll go up into the atmosphere higher and higher until it pops. And so what appears to have happened is the Earth had a single continent at one time, but then it popped. And when it popped, the continent split into multiple continents, and we find that some water that was under the surface of the Earth came out and formed the oceans. And if you look at the sonar records from Navy ships that our U.S. Navy has produced, they show the distance from the surface of the ocean to the bottom. And by doing that, they've been able to see stretch marks showing the stretching of the surface of the Earth over time.
Yeah, so I want to ask Eugene whether he's heard of this particular dissident theory, which is that the diameter of the Earth has actually been increasing.
Yeah.
And the whole reason behind the plate tectonics is not because the plates are moving around on the fixed Earth, but actually the Earth is blowing up like a balloon. And that is what causes the earthquakes and the plate tectonics.
Yeah, I certainly heard about this theory, and I've done a little bit of research into it, let's say. I've done some calculations. So my point basically is that in order for this to work, you definitely need a different theory of gravity. without it, it's not going to work because well, the point is really simple. If the Earth was small, then the gravity with the same mass would be much larger, right? Because the average density would be much more.
But that's an assumption. I don't think you can make that assumption.
Well, again, it's a reasonable assumption, I guess. I mean, again, according to the current theory of gravity. So if you have different theory of gravity, then yes, it might not be the case. But
well, there could be a different theory of where the origin of the additional material comes from. Because it could be that, it could be just that meteorites or just junk from space falls on the Earth, and that's what's making it bigger. In which case, it's increasing in diameter and increasing in mass, and then the laws of gravity could remain the same. I think.
Yeah, but as the continents on the Earth are only like 1/3 of the surface, you need to increase the size of the Earth quite significantly. I cannot make the calculation like off the top of my head, but it's like maybe 1.5 times bigger, about so. I mean, to transition from Earth being covered by land to Earth being 2/3 covered by water. That's a very substantial increase, and the amount of mass would be just huge. It's like the Earth's mass should have grown like maybe 4 times or something like that. So it's
yes, it would be quite large.
Yeah, I mean it's because obviously the mass rises as the volume rises as the cube, right, of the radius.
Now, me personally, my own pet theory on this is that basically inside the Earth is basically the sun, and that acts as a gigantic nuclear furnace, which is actually pulling matter out of space. Basically, the ether, I believe, is just this gigantic positron-electron source, and the middle of the Earth, as being a gigantic nuclear reactor, is constantly converting that into actual real matter, and so it's literally growing with additional matter. Would be my personal pet theory on why, if the Earth is in fact increasing in size, how that would happen. Of course, that's just idle speculation on my side, but it would seem to make more sense than a constant mass just growing larger in volume, as Bill would suggest, right? Because I don't particularly like that theory, because if I take a block of steel, it's not going to expand, by just sitting there. It's the mass has tensile strength, and generally speaking, it's not going to just decompress like a foam ball or anything like that. So that's why I would prefer to come up with theories that say that there's a way of mass accumulating inside the Earth.
What about the other bodies, like the sun, the other planets, the moon? Are they also growing, you think?
Yes, actually, the evidence from let's see, I'm getting some noise here. Let me see if I can mute. I think, Stefan, we're getting some noise from you. The people who investigate this, I mean, they've looked at Mars, and on Mars you can see these stretch marks. Apparently the largest canyon on Mars appears to be a stretch mark. The moon has these areas which also look like stretch marks. And curiously enough, when we finally got a picture of Pluto, it's consistent with this idea that the planet's surface is stretching and very large areas get infilled. These new areas get infilled with very smooth areas. And that was exactly what we saw on Pluto. Of course, we can't tell what's going on with the gas giants because they don't seem to have a hard surface. But even on their moons, we always see all this cracking, which is consistent with the body actually getting larger. So there just seems to be a lot of evidence that, as near as we can tell, this kind of activity goes on around the planets that we know about, at least. Although I was just reading something about saying that, like, maybe this was in your paper, that, like the planet Earth is the only place that has tectonic activity. And so I'm not sure if that's true. I mean, we have got like probes on Mars and Venus and anything else we can land on. And I'm not sure that there's no tectonic activity. I'm sure even the moon has moonquakes, but
Yeah, I have a point about it in my paper. So basically, as far as I know, the consensus currently is such that only Earth has really plate tectonics, but other places like the Moon and Mars, they have earthquakes. I mean, like moonquakes or Marsquakes for some other reasons. Like it's like some like localized faults or something like that. At least that's what I am aware of.
because you are familiar with like the very large canyon on Mars that just like stretches for like across like the size of the United States. I mean, that's not that's one of the things that the growing Earth people or would point at, saying that is equivalent to tectonic activity, I guess.
Well, yeah. Well, there are many theories about how this thing formed. I mean, there's electric/plasma universe. People who believe that it might have been some electrical machining of the surface. Like, let's say during a very strong solar storm. I mean, like a massive emission of mass from the sun. It might have caused very strong electric currents on the surface of the planet. So it might have been like a giant lightning strike or something like that, or even many lightning strikes, because Martian rivers are very strange. They don't look like rivers at all. They really look like electric discharge machine surface. So this dendritic pattern, it's also characteristic not only of water flows but also electrical flows, obviously.
So I think I've got a question. Stefan wanted to ask a question, so go ahead, Stefan.
Hello, can you hear me?
Yes, we can hear you.
I would like to ask questions to give comment overview. So, current theory of gravitation is general theory of relativity, which is accepted by all scientists. So, if you all criticize theory of relativity, saying it's not wrong, it's wrong, and then we have electrodynamics theory of relativity. Can you give the comment on LIGO gravitational waves? What did they discover? Because they got Nobel Prize.
Well, let's see here. It's very hard to hear what you're saying, Stefan, unfortunately. But it sounded that I'm not sure that you asked the question specific to Eugene's paper here about the biological origin of earthquakes, but you were asking something about relativity and
gravity.
About gravity.
You comment about gravity and expanding Earth.
Yes. So, what was your question specifically?
The question is, so since the general theory of relativity is wrong, because we have an electrodynamic theory of gravity. So my question is, LIGO detector detects gravitational waves which are predicted by general theory of relativity. So what did they discover if the general theory of relativity is wrong?
So are you saying you think that the theory of general relativity is wrong? And
no, I'm asking a question. What did LIGO discover?
So, as far as I understand, the logic of the question is such. So, if general relativity is wrong and like whatever electrodynamical theory of gravity is correct, then what did LIGO really discover?
Yes,
if that wasn't gravitational waves.
Well, it could have been a gravitational wave. The problem is is that a gravitational wave can be created very easily by any mass. So if I have let me see here, maybe I can try and demonstrate what a gravitational wave would. But just a second, I have to turn off. You see my extremely bright lights have just turned on, so I don't want to blind you guys. So let me go turn that off. Talk amongst yourselves just a second.
This is Bill. In the electrodynamic theory of gravity, it is superior to general relativity theory because it does not require the invention of dark matter and dark energy to rescue general relativity theory. It predicts precisely what we observe in Pioneer 10 and 11 experiments with gravity in our solar system, and also in the the velocity of the outer arms of spiral galaxies. That is predicted precisely by the electrodynamic theory of gravity, but general relativity theory misses it, and it requires, if you want to keep general relativity, you must say that dark matter and dark energy composes 96% of the universe, and regular matter and energy composes 4% of the universe. And I consider that a fudge factor, trying to rescue general relativity theory when you don't require it at all in the proper electrodynamic theory of gravity.
Excuse me, Dr. Bill. I agree with you on that, but my question is, what did LIGO actually discovered? So, general theory of relativity is wrong. They claim to discover waves that correspond to two massive black holes. So, if the general theory of relativity is wrong, there is no black holes in your theory of universe. So, what did they get the Nobel Prize, right? So, do you claim they are a fraud? They did not discover, or what? Can you give a comment on that?
The data is very weak, I guess you would say, and could be due to many other types of phenomena, but they're looking for something to justify the politically correct theory, and so they'll go for anything that seems to work until it's disproven. And so I think that we need to use logic and ask for consistency and falsify theories when the assumptions of the theory are using the assumptions are known to be false by experiment, but we don't say that if the assumption is known to be false, that falsifies the theory. We accept the theory, and I think we need to put logic back into the scientific method. And general relativity has 5 assumptions that are known to be false, and that should have falsified the theory. But we change the scientific method in order to keep the theory. We use what's called the existential scientific method, and that removes the role of logic. And I think that was a mistake. And even the postmodern philosophy of science still removes the role of logic, but they want to keep chemistry, physics, and all the different fields of natural philosophy separate, so that data acquired in one field, for instance, in chemistry, they discovered the electromagnetic nature of gravity. Well, that was not allowed to be published in any physics journal, because the people running the silo for physics said, we don't want that. We want general relativity. And so the people in chemistry say, well, you all are stupid. We've already done the experiments to justify the electrodynamic nature of gravity, and we can demonstrate it in our laboratories where we're doing chemical reactions. And but we don't pay attention to it. And we need to fix these things, because it makes science move in the wrong direction, but it does make it so that people can enter their politics into science.
Now, I've been scrolling through the wiki page on general relativity, and even after glancing through all of this, I still don't see an actual reasonable explanation of what the heck they're talking about. See, this is the problem with talking about general relativity, because you don't even know what they're talking about. They're just like talking around it, and there are these equations, but none of this is gelling for me as an actual explanation. So I don't know how anyone can look at this and seriously consider that this is actually really explaining anything. We have these equations, and presumably, they predict some things. And I don't know how, and this is the first point I was trying to make, is that I don't know, why in particular general relativity would predict gravity waves, because a wave of gravity could be easily created by if you take a lead ball and you bring it closer and then you take it further away, then if you had a gravity meter, you would see that as you bring it closer, the force of gravity would increase, and then if you take it away, the force of gravity would decrease. And if you did an oscillating motion, then that would create an oscillating gravity wave, is what that is. And theoretically that should propagate as like any wave would, and it's not anything particularly tricky, and I don't think it's anything predicted by general relativity. Now, like I said, I don't particularly understand what general relativity is, even after reading the entire wiki, and it's not even that long, but
Excuse
now,
me, Franklin, are you familiar with LIGO detector?
yes, actually, I visited LIGO, so I'm actually quite familiar with what they're doing there. And so this is the way LIGO works, is that they predicted, well, first of all, LIGO works by having two large arms and interferometer, and what they're literally measuring is a shortening of one of the arms. And that would be because if you increase gravity, that compacts things a little bit, right? And so that results in a physical shortening of the arm. So whatever they did, what they are literally measuring is one arm getting shorter than the other. That's what they literally measure. So if I were to, go on the end of the LIGO experiment and push on one end of the mirror, then that is the thing that they would be measuring. And that is the thing that they say general relativity predicts, but really anything could have predicted that. Like if I went and I took a truck full of lead and I parked it in front of one of these detectors, they should be able to detect that, because it's going to cause a compression of one of the arms asymmetrically, because they're at 90 degrees. So the gravity of that truck being parked there should shorten one of the arms. So that's literally what they are measuring. So what LIGO did is that they made some predictions, and maybe this is where the general relativity comes into play, that if they had two black holes and they were circling around each other, what kind of signal would that produce? So because the problem with LIGO is that you can imagine that they're trying to measure distances that are on the order of like an atom's width in like this 3 mile long arm of each experiment. They're trying to measure a change in distance, smaller or as small as the width of an atom, which I think is ridiculous. If you told me they could do that, I would say no way they could ever do that. But you can imagine that there's a lot of noise going on. Like every single time a car drives up on their driveway, they'll get a signal in LIGO. Anytime there's any earthquake anywhere, they'll get a signal in LIGO. So you've got all these signals coming into LIGO, and they can't look at everything. But what they're looking for is that they've got this prediction of what they think a black holes colliding into each other would look like, and they have their computers just sifting through all this data looking for just that thing, right? Now, what they detected was that they found that exact signal that they thought would happen. This signal happens in like less than a quarter of a second. well, actually even less than that. It's like a few hundred milliseconds. And so they saw that signal in both of their detectors. Because they saw that signal in both of their detectors, that's a good way to eliminate any like local causes. So they think that since they saw exactly the same signal in both of their detectors, that was a real signal. And that signal just happens to match up with what they predict would be a black hole colliding into each other.
Excuse me. So you think that their Nobel Prize is not legitimate? We should retract their Nobel Prize. Is that what you're saying?
Well, they detected their prediction. Now, me personally, unfortunately, with these kinds of experiments, it could be, yes, it's consistent with you detecting your black hole spinning into each other, but it could also be consistent with someone in Japan flushing their toilet. You know, that when you get something that has a lot of variety in it, I mean, it could have been something other than two black holes colliding into each other. Maybe there is some other phenomenon out there that doesn't have anything to do with black holes, but it does have something to do with gravity. You know, maybe if some space alien ship blew up somewhere in the vicinity of the solar system, maybe that would cause exactly that same kind of signal, right? So, but what's more significant, I suppose, to try and eliminate that is that they did actually take an optical picture of the location where they think one of these events happened. And optically, they thought they saw something that looked like a collision of two somethings. So visually, they were able to determine that not only did they get this strange, you know, whoop, whoop, you know, that's literally what it is, signal, that when they went looking into space, although with only two LIGO detectors, it's kind of hard to pinpoint where the signal came from. So, but I guess when they went looking in the general vicinity, you know, they found something that correlated with that event. So once again, it's still kind of iffy. I mean, they would have to go build another one of these multi-million-dollar, at least 3 of these observatories, so you could triangulate a more precise position of where these events happened, and then you could get a really good idea that, yeah, if you go and you get the signal and you go train an optical telescope on that exact spot, you should find something there, right? Something unusual. And so that's what they've been doing. So I mean, so as far as I know, that's what they've been detecting at LIGO. And they have actually detected a couple more events, like 6 or 7 or something like that. So,
one thing that you haven't mentioned is that there were something like 17 principal investigators on this LIGO project, and only 2 of them claimed they had found it, but the rest were told to agree because otherwise they lose.
Yeah, they would lose funding. Let's see, you guys still there? I think I lost Bill.
I can hear you.
That became only 2 of the principal investigators that were agreeing that they had found something. But they had to go, everyone was forced to go on because otherwise they would lose their funding for what they were doing because they hadn't really made that much progress.
Well, I have been to the LIGO facility here in Washington State, and I'll tell you, it's a beautiful facility. It's got some beautiful buildings. You walk into the control room, it's like, it's like that's where they launched the nuclear missiles. They got all the big screens, and they have a beautiful walkway, and they have a nice museum, and it's just like this scientific showcase, which is really cool. But they're clearly spending this like bazillions of millions of dollars to just kind of be impressive, right? It's and they have a lot of public outreach and so that. But results wise, yeah, they're kind of coming up short. If they didn't actually find this detection, they would have probably been out of business by now. But as it stands, because they need that third detector in order to triangulate the actual precise position of where these events are coming from, yeah, they'll probably get more money to do that. But it was really a public showcase. The way they set this thing up, right? It's like totally set to advertise and market themselves, I guess. But it is quite a endeavor to set this gigantic interferometer up. I mean, this is done like the highest vacuum that we can possibly manage on Earth in like a 3-mile tunnel. It's just incredibly expensive to do that, right? And you have to sit there and try and filter out all of these other signals. It just seems inconceivable. But anyway, getting back to Eugene's topic here on biogenesis. So I don't think, Eugene, you particularly responded to my question of why we would need to look for a biological explanation if the geophysicists are convinced that they already have the answer. I mean, I guess that's what the dissidents always. That's the problem with the mainstream versus dissidents. So dissidents come up with some alternate explanation for something, and we come up with something which sounds crazy. So what would you say to those people?
So technically, you are correct. Like this, let's say, theory or a hypothesis or whatever you want to call it, is not needed in this sense. Like there are explanations, but at the same time, well, I mean, I just had this idea and I wanted to research it, and it seems viable. So that's all there is. And I might tell you that I am not convinced that it is correct, but it is, coherent. It is self-consistent. So I had to publish it because, well, who knows? Maybe it's actually correct. So you're absolutely right that it's, strictly speaking, it's not necessary.
Also, one should notice that if you have the idea the Earth is expanding and there are cracks associated with the earthquakes and those things, biological entities in life can go into those cracks and live there and populate them, but they won't be where the cracks aren't because they're not they can't get through the material, and so it could very well be that the biological evidence we're seeing could also be explained by the cracks in the surface, allowing the biological entities to live deeper into the surface of the Earth.
Well, that was one of the arguments that I give in my paper, that like 90% of all the earthquake activity happens in the Pacific Ring of Fire. That's basically the edges of the Pacific Ocean, right?
Uh-huh.
And this is basically one huge trench, like many kilometers deep, that encircles the ocean. So one of the ideas I've had is that indeed those trenches allow microorganisms to, let's say, penetrate across to larger depths, just because of the general topology of the place.
Mm-hmm. Yeah, I think that you have all these things have to be taken into account.
Well, I think I wanted to make a comment on this whole self-consistency thing, because as dissidents, I would argue that self-consistency is grossly inadequate to either to prove a theory, or to convince other people. Actually, self-consistency, I guess, would just be like the first rung on any ladder to the actual truth. Because even as dissidents, I would hope that we are trying to actually seek the actual source of truth and are not just merely obsessed about trying to promote our pet theories at any cost. Although it would seem that that's what we generally do. I'm going to promote my pet theory at any cost, and I'm not going to listen to anybody else. Or, it could be, I seek the truth, and if my pet theory is not as good as someone else's pet theory, then I should go and adopt their pet theory. But I think what mainstream wants to see, though, is that we all start out as theoretical physicists, and as theoretical physicists, we can propose anything we want. And things can be self-consistent, but that could be like science fiction. So, for example, we have the entire universe created by Star Trek. And they have things like warp engines, and they have transporters, and they have phasers. And internally, all of that is perfectly self-consistent, right? There doesn't seem to be anything wrong with that. But it is, in fact, all completely fake. There's nothing at all real about Star Trek. But it does inspire us to create, Star Trek things, like our cell phone works just very much like the Star Trek communicator. So that has gone from like science fiction to actual science, right? But and so that's a hard science now. But when it first came out with something like that was certainly self-consistent, that you could have some kind of device you could put in your pocket, you open it up, it communicates across long distances. And at the time, there's just absolutely no way anything like that could have possibly existed, right? But it was self-consistent. And it eventually turned out to be, say, true. And now we're getting things like, our iPads start to look suspiciously like the tablets they're carrying around and stuff like that. But I would say the point there is that self-consistency is not sufficient to be, I think, taken seriously. Your theory needs to start making predictions, specifically predictions which can actually be experimentally verified. And or making and what's more important is making predictions of phenomenon that have not yet been observed, because I'm usually pretty highly critical about theories which make extremely high predictions, things like the gravitational constant, because we already know what the gravitational constant is, or we already know what a spectra is, or we already know any number of experimental results. And unfortunately, we can always use our confirmation bias to change our theory to exactly match any observed result. So that's why I think it's probably far more convincing to come up with a prediction of something which hasn't been observed. So for your theory here on the biological origins of earthquakes, perhaps you would predict that in like the deepest hole we've ever drilled in the earth or something like that, that if we examined it for this kind of microorganism, that we would find it. And if that were true, then that would kind of dispel probably, like, the first objection would be that it's just way too hot. I mean, it's as you get into the depths that we think earthquakes happen to, that's like molten rock, man, and there's just no way anything of any biological nature could survive that. So if you could, I don't know, find some biological activity in like the lava coming right out of Kilauea in Hawaii as it's spilling out, then maybe that would be convincing. So Eugene, you got any evidence like that?
Yeah, I actually have a whole section about volcanoes, and there is plenty of bacteria that are found in lava. But I mean, theoretically, supposedly, these bacteria arrive there after the lava kind of cools down, but they might be there initially. Because, and actually, like, there is evidence that the lava outflows, let's say, they change the local population. Like, these are different species, let's say. But, of course, yeah, I agree with you with your general point that it's not enough to just have a theory which is internally coherent, etc. I would say that what is needed an additional thing that's needed, always needed, is just a simple, pragmatic thing. Like, if your theory allows to explain something which none of all the other theories can, then, you're in the game, basically. But I haven't yet found any specific things, well, except for the obvious ones, like you say, like basically we can drill and we'll find life anyways, like however deep we go. Well, that's kind of obvious. But literally today I was thinking about maybe like proposing an experiment for, let's say, those people who work with this deep subsurface biosphere. Like the deepest I think we have found life under the surface was like maybe 5 kilometers or something. There is also a problem, you see, with actually detection of these microbes, because many of them cannot even be, culturized, or what's the proper word? Like, you cannot grow them. That's a big problem. And I also cite one paper in my paper, which says that the absolute majority, like 95 or maybe even more % of all the microorganisms on Earth were not detected because they cannot be grown in a laboratory. So you basically take a sample, you like put it in a sugar dish or something like that, and usually it grows, but at least supposedly. But the paper that I cite claims that most of microorganisms actually don't grow in these conditions. And in particular, one of the problems with the ultra deep biosphere is that it's just so slow, it's like typical time of operation is thousands of years. So the cells just don't divide, so you cannot grow them as quickly, because, well, they are adapted obviously to these super extreme conditions, super like energy limitations, etc. So they just cannot even grow in like normal good conditions anymore. So yeah, but yeah, I was thinking about proposing an experiment, like in the laboratory, if you like literally just take a let's say a vessel with something with rock, let's say, and you like put these microorganisms in those rocks, and let's say you try running a current through this system, maybe you can detect some, microseismicity, so to speak, produced in that way. So that would be, I guess, an experimental confirmation of the theory. At least it doesn't seem like this should happen otherwise, any sort of like shaking of the thing, even if it would be minuscule, like maybe micron size or something like that. But yeah, I'm currently thinking about that. Like,
well, I think what you should do is that you should go ask those Kilauea scientists who are pulling lava out of that thing all the time to take a sample right out of the volcano in a way that would completely keep it, isolated, and then expose it to, and then let it cool, and then go see whether you can find your microbes in there, in whichever way. That's something that they could easily, just have them take a sample, immediately seal it up, and then just like stick it in super sterile water or something like that, like they're doing a space shot, and then see whether they can find any life on that rock, I guess.
Yeah, well, one of the problems, an obvious problem, is that you can't actually make anything super sterile. That's another problem. Like, these guys that have detected these new microorganisms that can live at 420 Celsius, they actually say that, well, it means that our usual ways of, let's say, decontamination, like, again, heating up stuff, etc., they don't really work that well. I mean, they eliminate like 99.999% of the stuff, but there's still some stuff remaining, There's always some trace amounts of bacterial endospores, like they're literally everywhere. and they might survive for like millions or hundreds of millions of years, and then if they arrive at the whatever the appropriate conditions, they turn into a vegetative state, so they kind of spring back to life. So in this sense, actually, I think our probes have already sent these bacteria to the moon, to Mars, and to all the other places. It's just that probably the conditions there might be not fit yet, at least, for these bacteria to come to life. I mean, for these spores. But they're most likely they're there. And yeah, like think about the astronauts who went to the moon. I mean, like every human has like tens, even if not hundreds of species of bacteria living on their skin, literally, right? I'm not even talking about, the gastrointestinal system, etc., where there's like kilograms of biomass, of these symbiotic bacteria. So these bacteria are also on the moon already,
So we've created the first Martians, and they are us.
Yeah, sort of.
Well, that is an interesting point. I mean, that's an interesting point that
Yeah, by the
there are
way,
these bacteria that are hard to detect. But you
Yeah,
think there are going to be so many of them that they can cause an earthquake? Do you think they're causing an earthquake by an expansion of their mass, or what would be the mechanism? Even if they're like billions of microbes beneath the earth, I don't think that they would trigger earth movements. Why would they trigger earth movements?
well, there's, let's say, a couple of possibilities that I explore in my paper. I'm not like entirely convinced myself, like which one of them is true. Like one possibility I can see is like if, let's say, an earthquake is inherently an electrical process, like it's something like underground lightning, in this sense, if these bacteria actually feed on telluric currents, they might invoke some process like that, perhaps. So this is one possibility, and the other possibility is just some collective motions, let's say, due to whatever metabolism they might have. So I actually cite one of the papers there which have detected what they call, literally in the title of the paper, earthquake-like motility of
Okay, I have to
bacteria.
go take care of something, but you guys carry on, okay?
Okay.
I'll give a few comments here. I've been studying these issues myself, and one of the interesting observations I made was of limestone coral. And limestone coral grows something like a tree, and it has something like a tree ring, one ring for each year. But one thing that seems to be a little different about the limestone coral is it has a ripple in the ring, and the ripple has a measurement of the number of days in that year. So if you look at the current limestone coral that are being formed right now, they have 365 ripples in them. But if you look at the older limestone coral, they have 481 rings. Between they go from 365 up to 481, but the oldest ones that we've seen so far have 481 rings, and that means that the Earth is rotating faster in the past, but it has slowed down, and that indicates that it can only happen if the Earth is expanding, because or you have to add a huge amount of mass to the Earth on the surface. But we don't see the evidence of that much mass coming down. We have some, like I've been to some of the ancient cities of Europe, and you'll find that where there used to be steps up to the building doorway is now even with the surface of the Earth, which shows that there's been a 20 or 30 foot difference over thousands of years. But that's not going to explain the expansion of the Earth that we have measured. And so it looks like some other process other than meteors and stuff like that coming down to the surface of the Earth to explain the expansion. And so I think we need to take all this data into account. And what I don't like about many of the scientific experimenters in these fields is they deliberately ignore some of this data. They say, well, it doesn't exist. I don't believe it's the data. But other people who looked at it and who are more experienced with it say, well, it's perfectly good data. And so anyway, I just mentioned that. And the other thing is the age of the Earth. I'm a nuclear physicist, and the nuclear decay methods that we've been using are not done right. For instance, I'll just give you one example. We have a mineral on the surface of the Earth, and it has some uranium in it, and it's got lead. And we assume that in the past, it just had uranium and it decayed to lead. So we look at the amount of lead, and we see the amount of lead is approximately equal to the amount of uranium still left. And we say, oh, the uranium is decayed. So that gives us a very old age for that mineral. But if you look at it under a microscope, you'll see what are called radio-halo patterns. And these patterns identify what was decaying into lead. And you'll see that there's a ring in this pattern for every alpha particle that was given off in the decay sequence. And you can look at the number of these rings and the diameter of the rings, and that will tell you what was decaying. And when you look at that, you say, oh, not everything is coming from uranium. There are 50 other radioactive isotopes that decay to the same isotope of lead, and many of those are present. And so we ignore that, because if it doesn't agree with what you want politically in science, you ignore it. And but it's not proper. It's not the correct way to do science. It's not logical, but we don't do it that way in science today. And I think that's why we exist here as alternative scientists. Is we've discovered that in one way or another in whatever area we work in, and we're trying to improve upon science and a scientific method. And Isaac Newton is the one that told us how we should be doing this. But people are ignoring what he said. He was telling us how to combine the axiomatic or logical method with the empirical or experimental method. And when you do that properly, you falsify theories if the assumptions of the theories are known to be false. And unfortunately, all of our major theories of modern science have assumptions that are known to be false. And so our theory of quantum mechanics, our current theory of electrodynamics by Albert Heaviside, not the backspin version, but the Heaviside version, they have assumptions that are known to be false. And you have relativity theory has assumptions known to be false. Big Bang theory has assumptions that are known to be false. The way we date the ages of things on the Earth that we see are known to be false, those assumptions. So just many areas that we need to work on. And but when you mention it, and I did once when I was on the faculty of Catholic University, and I was fired in 24 hours to mention it at an American Physical Society meeting. And that's what they do. And we, and in the old organization we have, the NPA, at one time there were hundreds of people who lost their positions at universities when they thought that they were moving in the right direction to improve science, but they were politically incorrect, and the people who wanted to maintain political correctness got them fired. And so it's a problem we have to deal with, and we need an independent source of income if you want to do it for very long. Because the people who have worked with me in publishing papers in theory of the nucleus and theory of the atom and theory of elemental particles, they have lost their university positions because they disproved the current theories, and the proof was valid. And the scientific community just couldn't stand it. They said, get rid of that guy and don't let him ever get a job at the university again in the United States of America. And that's what they do. And if you've had that experience, you know what it's like. If you haven't had that experience, well, I hope you don't. But you could if you have a university position.
Hello,
Yeah,
can you hear me?
yes.
Hi, with regard to the biological activity causing fissures or expansion, here's a simple experiment. If you have a concrete driveway or sidewalk with some cracks in it and some plants start to grow, it seems to me that the root system's expanding, actually perhaps molecule by molecule, tends to disintegrate the concrete and make the crack bigger. And so that's just a common observation that many of us have seen probably occur. And I don't know whether that's actually true, but it seems to me that where root systems get into a crack in the concrete of a sidewalk or a driveway or whatever concrete slab you might have, that biological activity can produce fissures, and the whole process is a slow one, perhaps, as I said, molecule by molecule. Now, you might say, well, what I'm talking about here is root growth. But what the other gentleman that I see on the screen was saying is like bacteria or single-cell organisms. But still, if they're growing and they get run out of space, one could say perhaps, they're applying a pressure to the surrounding non-biological material to increase the fissure size or be a factor in causing a fissure. So as a change from the highly intellectual contribution that Bill Lucas just made, I'm bringing this down to grass growing in cracks on concrete sidewalks. So if you're looking for experiments, I mean, it seems like a lot of us have it right in our yard right now.
I think you brought out some points, but when I look at my driveway, I used to have a cement driveway, it was cracking, I believe, due to some other factors before the grass started to grow. And then the grass and other things started to grow and make it worse. So,
okay, so your impression, Bill, is that, to confirm my impression, because mine is just sort of an anecdotal observation where I'm saying it seems like this biological activity, the root system of whatever plant is growing in a fissure. Yeah, you have to have a fissure there to begin with. That's where the grass is going to grow. But so you're confirming that you've seen things like what I've seen.
yes.
I've assumed that the grass root system growing into the fissure is actually applying a pressure, which, again, it could be molecule by molecule, is sort of disintegrating into a powder what was a relatively solid form, i.e. the concrete slab. So I rest my case.
Yeah. But you would think it would do it in more places than it occurs, but it only occurs in certain spots in the driveway or the sidewalk. And so it's not uniform. I guess that's what I would say. So I think that the original crack had some other reasons for it, but then this made it worse.
Yeah, granted. Yeah.
Well, the cracks might appear just due to thermal expansion and contraction. That's even on a daily basis.
Or it could
you
be
have a hot.
your car when it goes down the driveway or a truck or a heavy thing that happened to come in one day cracked it. And
Yeah,
I-
exactly. So like a meteorite falling would produce some micro cracks here and there, which might later be expanded, etc., etc.
Yeah. But I would expect living things to go into these cracks, no matter what the source is, and so you would see some kind of life in them. And but to say that caused it from the scratch, I don't know that we can say that too easily. But maybe you could make an experiment where you make the driveway with no cars or anything on it, and see if it cracks. But just do the living.
Yeah. Okay. I just wanted to mention.
my comment was that of root systems growing in an existing crack. I mean, I've observed that where there are no cracks, the grass does not grow. I mean, there is no grass growth. So yes, you have to start with a crack, and then the grass starts to grow in there, and the root systems expand. And it seems to me over a period of time that where that happens, the fissure is worsened or made, that it does increase the crack, as it were.
Yeah, I think some of the ingredients in the cement or the concrete are used up by the living thing, and that causes
Exactly.
it to disintegrate, and they get worse.
Yeah, so I just wanted to add one interesting experiment that has been done like a few years ago. So I can send you the link probably, but anyway, the long story short is that people have observed, to their own amazement, that if you have a vessel with some like sandy substance, let's say a sand or even a flour or something like that, and if you shake it so that the cracks would appear, somehow this generates quite a lot of voltage. So they measured the voltage. I don't know who came up with this idea, but somehow they did. So they measured the voltage, and it was like 200 volts in this system by just producing these cracks in the sand or flour or any other substance like that. So what I'm thinking about is that maybe the reverse process might be happening. If you apply voltage, you get the shaking, something like that, and you get the cracks and etc. And it might be biological, but nobody really knows how it happens. Like, why is this voltage even there? It doesn't make any sense. Maybe it's the atmospheric electricity.
We see a tremendous voltage coming down at the pole, and then in the thunderstorms occurring more close to the equator and those other places, we see tremendous amount of electrical power going up through the clouds and all the way back to the sun. And so there are routes there. And when we first started putting satellites up, we could see them, and we didn't expect to see that paths of power flowing from the surface of the Earth back to the sun, and from the sun to the Earth and coming down at the poles. So there is a lot of power going on. And the amount of power that comes down at the poles is larger than all the electrical power plants that we have on the Earth. So it's a big amount. And
Yeah.
we don't
So-
know how much we should know about that.
That's another argument that I give in my paper in favor of my hypothesis, is that if you think about the sources of energy on Earth, obviously it's the sun mostly. So the sun gives us this electromagnetic radiation, which is the visible light at sea level mostly. And we have like a whole biosphere built around this, right? The green plants actually the biggest amount of biomass on Earth. I mean, not only plants, but plankton, etc.
Yeah.
So, but anyway, the largest reservoir of biomass directly feeds on this electromagnetic emission. But there's another thing that the sun supplies, and that is charged particles, essentially telluric currents. Again, Birkeland currents in the poles, and Featherston currents, and eddy currents, etc. So my claim was that if life did evolve to, let's say, feed on this electromagnetic component, the radiation, why wouldn't life evolve to also take the energy from the currents, which is another source of energy from the sun, basically. So I claim that this subsurface biosphere might feed on these externally driven currents. So this is the idea.
Yeah. Other comments or questions that people might have?
Can I ask one question to you, Dr. Hill?
Go ahead.
You said that quantum mechanics is wrong, and Heisenberg uncertainty principles are not valid. So my question is, if they measured Casimir force on virtual particle in vacuum as consequences of Heisenberg uncertainties, can your theory explain that?
I'm having a little trouble hearing what you say. Can you turn your volume down on your side of the speaker so that we can hear without the echo?
Excuse me, I did not hear you. Can you repeat?
We're getting an echo back from somebody, and if you mute yourself and you still hear and you don't hear the echo, it's on your side. If you when you're unmuted, you hear the echo, then you've got to turn the volume down on your speakers or whatever, or use the earphone to hear. But go ahead and try again.
Is it now better?
Yes.
Okay, so I have asked the question, can you give comment on quantum vacuum as consequence of Heisenberg uncertainty? Since you say that the Heisenberg uncertainty principle is wrong in your theory, in your papers, but we measure Casimir force and virtual particle annihilation vacuum.
Okay, I have been working with the electrodynamic approach, and it turns out that if you solve the 6 empirical equations of electrodynamics, that's Gauss's 2 laws, Faraday's law, Ampere's law, Lenz's law, and Lorentz's law, simultaneously, you find that the simplest structure, that the solution to the 6 equations is a toroidal ring called a soliton, and that all quantum effects are due to the properties of the soliton. The soliton it's in the shape of a toroidal ring, it has tensile strength, and it is continuous and uncuttable. And it can support waves within the toroidal ring. And you can do this experiment yourself by making a toroidal ring of something like just a what do you call it? These spring type things that you use to go up and down steps and stuff. You make one of those continuous by soldering the ends together, and then you find that you can have standing waves, or standing wavelength is circumference of the ring, or twice the circumference, or 3 times the circumference, or 1/3 or 1/4. And so quantum mechanics does not allow that to be done with electrons going around the nucleus of an atom. You only have the wavelength is in multiples of one another, not 1/2, 1/3, or whatever. And so the current theories of the atom, the quantum theories of the atom, miss half of all the measured empirical emission lines of all known atoms. Half. And these lines are in the extreme ultraviolet. They have been measured by NOAA and NIST, and they can be measured to higher precision than, and they're measured in space. They can be measured to higher precision than the than the older emission spectral lines that they measured before, which were only part of the spectral line. And so anyway, this work that has been done and these measurements that have been made, they falsify the Dirac, the Schrodinger, and all the quantum theories of the atom, because they cannot predict half of all this experimental data. They can't predict any of it in the extreme ultraviolet. The theories are just incapable. And but the electrodynamic theory in terms of solitons predicts every single one and no extra. It predicts exactly what we can observe. And so that's very interesting. And but the way that we get this is we solve all the empirical equations of electrodynamics simultaneously. We don't choose a subset and throw away the ones we don't want to use. And that is what was done by Oliver Heaviside for political reasons in science. And you have to study the politics of science to know what those political reasons were. And I'm not going to bring them up here, but they are known. And they're not allowed to be taught in any public school in America. You will be in trouble if you do that. And if you're a teacher, you'll be fired. If you're a principal, you'll be fired if you allow it at your school. And you can't receive any federal aid if you don't follow these political rules. And they call that the education framework. And you can go online and see the education framework of what you're allowed and not allowed to teach in every course from kindergarten through the PhD. And in the state of California, there's a book for each subject, for each grade level, and for each year of college and university. So you can see all of that if you really want to know what it's about. So it's an awful lot of stuff. But that's how that's enforced. And if your school doesn't follow that, no one can get a loan for education to go there. And you can't receive any federal aid of any sort, including your cafeteria. You can't get the reduced price foods that you can serve in your cafeteria. You have to pay the normal market price. So,
excuse me, Bill?
Yes.
Hi. We've discussed at several points during this session, the censorship, and you've done a lot of that, that is occurring in modern day science. So the question occurs to me, just to throw out to those here, how can we as a little group, like Franklin said, we're a small percent of the dissidents and so forth, how can we enlighten the general public more about the fact that censorship in science is so prevalent and so in many cases vicious? That's my question. How can we do that?
Well, there is one group called ABECA, the Religious School Group, and they're not eligible to receive any federal aid, and they publish history books that give that information in their history books, which they teach in high school and college. And but you have to buy that book, and they are there are many groups going after them, trying to shut down their publication of these books. But that's the way to do it, and you have to be. If you had a school building and you were teaching people there, it would be harder than if you just have curriculum that you're selling to people that they can read. But yeah, and they don't make it terrible. They just tell you what's going on. I mean, they don't tell you what's happening to hundreds of people every year. But my wife went to her 50th reunion for her high school class, and many of the people in her high school class became high school teachers over the years, and all of them are very unhappy with this turn of events in the educational system. It wasn't there when they were growing up, but it's there now, and they hate it, and many of them quit their jobs because they didn't want to participate. And so that's you can get some information on that. Some people are publishing some material related to that. I've done a few TV programs on that, which were aired worldwide, and so that's something that can happen. But when you hear politicians talk, and they're talking about running for office, for president or Congress or whatever, they never mention these things. It's something that parents don't like. It's something that people who are teachers don't like, to have to conform to this education framework, and it's part of Common Core. And so we have it everywhere, and it was set up in the founding of our country. It was set up by Thomas Jefferson and James Madison when they set up the Constitution of the United States and the Bill of Rights, and they set up a wall of separation between basically truth and science. What they called it, church and state, is what they called it. And that's how they got set up in colonial days. And of course, if you're familiar with colonial history, you remember there was an established church supported by taxes in every colony, and all the churches were disestablished. And then there were what we call the first and second great spiritual awakening in our country, and the formation of many churches, Baptist, Methodist, Presbyterian, and many other churches. And the people who didn't like religion wanted some way to combat it. So the wall of separation between church and state enabled them to combat all the religions. And they did that by requiring the schools to teach that those religions are myths and they're not true. And that's what they're doing. And let's take a few examples. What's the age of the earth? Billions of years. What's the age of the earth according to the Bible? 10,000. What's the origin of the universe? The Big Bang. Nothing to do with creation. How old is the universe? 13 or 17 billion years. And then what is driving everything in the universe? It's quantum mechanics and statistical versions, and everything that's going on is related to quantum mechanics. But if you use the electrodynamic version of science from the empirical equation, you discover that everything that occurs in the universe is a function of the electric field, and the electric field origin, according to the Bible, is God. And the first people in the days of Maxwell who worked in electrodynamics, they didn't talk about the fields, they talked about the spirit of God. And people did not like that, and they wanted the wall of separation, and they went for it. And so that's how we got where we are today. And if you investigate that very much, you'll find more and more of it going on over time. And so, anyway, there are textbooks that cover that Becca curriculum, and you can get that for history, and they cover that in their history books. But no public schools in the United States, and no religious college in the United States teaches that, because they all receive some kind of federal aid.
Excuse me, Dr. Bill, can you give us the name of these textbooks you mentioned?
Say that again. Name of the book?
Yeah, name of these books. Can you write it or?
Okay, it's the curriculum and books created by Becca. I think it's EKA. I think that's the spelling. You have to look it up on the internet. It's people use it for homeschooling. In my family, we used it for homeschooling. That was how we learned about it. We went to public schools, all of us, my wife and I, and they never mentioned it. And but in using homeschooling, they in their history books they cover that. And so anyway, you can see that, and I suspect if you look up stuff on the first and second great spiritual awakening in America, these were the revivals that were held up and down the colonies. You see the impact that they had. And my grandfather was one of the last participants in that. He was the pastor of a mega church in Cincinnati, Ohio. And this mega church had a chapel at all the major streetcar stops in Cincinnati. And while he was pastor for many years, they averaged 1,000 professions of faith per week. And there were people that hated that. In Cincinnati, things like prohibition got promoted because of all these people becoming more responsible and that sort of thing, and other people didn't like it, and so they opposed it in any way they could. So, but if you look at our Constitution, we're one nation under God and all that kind of stuff. Well, we don't really emphasize that too much anymore. And and in Great Britain, you still have established churches, like the Anglican Church. But in America, we don't have established churches. Every church has to support itself. No taxes support them. So, any other questions on that? Because we're getting close to our closing time.
Yeah, we're getting close to our closing time, so I think I'll probably wrap things up. So thanks for everyone participating today. Thank you, Eugene, for bringing us your topic on the organic basis of earthquakes. So I hope that we had some good discussion for you there. And once again, we have your paper here from Earth Arvix. And I would encourage people to, take a look at that and, just think critically about some of the various ways to address what may be the problems with this theory, and perhaps to collaborate. So thanks for Eugene bringing that up. And, he was able to bring that up by just sending me an email. And we'd love to have you present any ideas that you have. So if you guys are working on something and you want to just bounce it off some people, then I would encourage you to go ahead and send me an email or just show up to the chat here. And you just have to get on to the live link and we can have you on the show. But I think that will do it for this week's episode of the Science Chat, and hopefully I'll see you next week.
Okay, thank you.
Bye.
Goodbye.